Slightly harder day than normal. We're all a little tired, but we'll get through it. Here's our second live recording session going. And we're now in section 11.3. Our goal is to, well, do some meaningful work in section 11.3. I'm not going to try to race through it. We'll work at a normal pace. It's an interesting test we're looking into as well. And it's interesting because when you look at the summary for tests, this is a document supplied to you on exam 3, and probably the final exam as well. Integral test is way at the bottom because, like we've said a few times, it's a test you usually want to use last. When it works well, it's the best test ever. But there's so many problems where you'd really want to do something else, like a P-series test is extremely fast. You don't integrate, you don't set up an improper integral. But when things fit into this domain, it's the best way to go. So let's give this a try, folks. Here's the good old integral test. And it's a really nice test in the sense that this is something we've already done before. We're dealing with this kind of proper integral. It's improper type 1. So it's a callback to that section from chapter 7. We do have a lot of hypotheses to make this test work. F has got to be a continuous function. And that makes sense because that guarantees integrability. Well, maybe. It is improper, right? It guarantees integrability if we have finite numbers in the integrand. It must be a positive function. And at the same time, it has to be a decreasing function, all in the domain from 1 to infinity. And then if you have that, there's two things that can happen. The integral can converge or it could diverge. But we're also tying it together with the series itself. So once you define the function f, you go to the sequence that you're dealing with that you eventually turn into a series over here by including the summation. And on the sequence, you define the nth term to be the function value at n. What you're allowed to do, because n is in the domain of this function from 1 to infinity, it's just an integer value. Once we've made that correspondence that the function value matches the sequence on all the integer values right here, the convergence or divergence of the series is now completely tied with the convergence or divergence of the improper integral. So if the series converges, so does the improper integral, and vice versa. That means we can discuss convergence divergence by just integrating here. Convergent here gives us a convergent series, and divergent here will give us a divergent series as well. So that's the whole test. You know, the challenging thing about it is to really explain how it works. So that's why you see all this white space down below here. We'll give a sketch to get a feel for what the test is trying to convey, and then we'll practice it out down below. Any questions first with just the statement of the test so far? Okay, let's begin then on case 1, or case I as it's written, where the integral from 1 to infinity, f of x, dx converges. Then we'll look into case I, where integral from 1 to infinity, f of x, dx diverges. So first graph down below, let's start with the function maybe. The domain of this function is very particular, 1 to infinity, but that's only matching this one. If we started at 0, we'll go from 0 to infinity. If the sequence starts at 12, the domain will start at bracket 12, go to infinity. So there's always a matchup on that index there. Let's start at 1, 2, 3, 4. That should be plenty of values. Function value takes on some point right here. Solid dot to match up with the bracket. And because it says it converges, this is what the sketch would look like for something that appears to converge. It has to head towards the x-axis rapidly. That's giving us convergence now. So if we took a look into this integral and compare it against the sequence, we can draw in something pretty interesting. So here comes in this sequence next. The sequence values, well, it starts at 1, so we'll have a value right here, completely matching the function value. Here's a1. That's to this correspondence here at value 2, It matches the function value, so we have a point on the curve. Here's A2. But it gets really hard to specify from then on out. Here's A3, and so on. I'll stop at A3 since we're losing space to specify the fourth one. Now, next thing, let's go with slightly lighter green color on this. If this converges, I want to express that this series right here, let me double check my notation. That's kind of odd. You know what? It's got an I here. You could make that work, but only if you put an I right there. I've never noticed this before. Let's correct this right here and now. That should be an index n to match up with the summation an. It's those little things, you know. When you zoom in enough, sometimes you notice them. That should be an index n as well to match up with an. And now let's take this back and draw out the terms of this series right here. Here's the very first term. The area equals A1. It's kind of a weird thought, right? The area itself is A1. That's because the height is right at A1, and the width is guaranteed to be exactly 1 because of the sequence. The width is always 1 from each rectangle. So you can think of areas as actually expressing the terms themselves in this diagram. So this area right here equals A2 as well. This area, getting really hard to draw, is A3, and so on down the line. So the areas are the sequence values themselves, which means they're the terms in the series. Except, notice that there's a one-off in the conversion. This area that I've drawn in doesn't actually start where the area under the blue curve begins. So I'm going to write out something that looks kind of funny. Let me know how you feel about this. I have summation n equals 1 to infinity an. That's going to be less than or equals to, depending on if this was 0 or non-negative, as we see right here. Summation as we go from, or hang on, let me think about this. Oh, the estimate would go in a different way. I think I need to start my argument by really beginning saying n equals 2 to infinity in summation of ai, or an, is going to be less than the integral from 1 to infinity f of x dx. Seems kind of awkward. I would like to start at 1 because that's where this starts off out, right? But really, the areas under the blue curve starts off at A2, then it's A3, and so on. So I'm really forced in saying my series starts right at that value. However, here's another really important concept. Convergence and divergence of any series whatsoever does not depend on finitely many terms. So in other words, if an ordinary series like this one, if this diverges, it still diverges if you start off at 10. The fact that we deleted a bunch of terms, 9 of them, doesn't affect the divergence. If this converges, but we decide to start off at 2, still converges. All we did is we lost a single value there. And it's awkward. We needed to start at 2 because, again, like we said, that's where the blue curve starts. But this is already kind of the magic of the integral test. Something that we're trying to determine convergence or divergence on with infinitely many terms is bounded. It's bounded by an improper integral right here, and that improper integral is equal to limit as t goes to infinity, integrate from 1 to t, f of x dx. But that limit equals L as a real number because we said this part converges. So infinitely many term sum is less than some finite number, this immediately implies summation as we go from 1 to infinity, the full series, an, must also converge. It's all due to that estimate right here. And I should still say less than or equals to, just in case the function is a very, very strange one. So if we can give an estimate that the summation is less than some finite number, any finite number, as long as it's not infinity, we have convergence down here as well. So it's kind of a weird graph. Does that make sense on how that estimate right here occurs? Okay, so that's the convergence picture. We need to turn it all the way around and say, what about divergence? What does the picture look like when we diverge? We're going to not start at 2 for that picture. We'll start at 1. We had to make a hack because of this one not fitting in with where the curve started. So here's our case 2. Let's look into case 2 in view of how it changes from case 1. Same kind of graph we're dealing with. But this time in case 2, we're saying the improper integral now diverges. So we'll draw a picture that kind of conveys that once I decide on how far to scroll. Oh, hang on, let me fix these windows a bit. Okay, so let's start at 1, 2, 3, and 4 like before. I'll let the curve start here. And remember, it has to be a positive function as one condition. It has to be continuous, and it has to decrease as well. But this one's decreasing at a rate that looks like the integral is really divergent. It's just not decreasing very fast whatsoever, and that's our y equals f of x. We place under it the terms of the actual series that we're comparing against. We're saying this one is divergent, but look how the graph goes this time. We're not going to throw away area A1 anymore. We're actually going to use it. And here's how it gets plotted in. Start with a vertical line going all the way to the top, A1, exactly what we did before. But you know you can make the rectangle go to the left like we did. That's only if you want to show convergence. Or you can make it go to the right, like we will do here. The area is still A1, no matter if you made it go left or right. So here is area equals A1. Then right at 2, here's A2. And this curve goes like this. Area equals A2. And this just keeps on going and going. Let's make this be our last one. Area equals A3, and so on. Dot, dot, dots, just to say the pattern continues for all time. But now this time, with the way we drew our rectangles, they lie specifically above the curve. We know the curve diverges as well, so we can say this. Summation, as n goes from now 1 to infinity of an, so we're looking into the total series this time. By the graphs we see here, we have an estimate going the other way. Greater than or equal to an integral from 1 to infinity of f of x dx, which is again the limit as t goes to infinity, integrate from 1 to t f of x dx. But this one diverges up here. That means the area that we pick up under the blue curve is infinity. And yet, look how our estimate goes. The sum of the series is greater than a value that's already infinity itself. That means the series, summation as we go from 1 to infinity, an, must also diverge. So up here, I forgot to say one important conclusion. I should have said converges. And let's just extend the yellow. That's why the series must converge. Up here, because of the infinity, I should also say diverges. But that conclusion of diverges is for the integral right here. The separate, more important conclusion that we care about after running the test is that the series itself must also diverge as well. So that's a pretty bold statement. It's actually maybe the major fundamental reason we wanted to look into improper integrals in the very first place is because of how it ties in with series right here. So the short of it is the improper integral from 1 to infinity, its convergence or divergence is always equivalent to what happens with the series itself. They always converge or diverge in the same direction. Any questions at all, folks, with the essence of that integral test through graphs? Okay, now that we have a pretty good feel for this just by considering the graphs, next problems we're going to take a look into is just seeing how to run through the test, showing all the full steps. So down below, here's the integral test just restated for easier reference. And this will be our first full problem. Notice how nasty it is. N is not an exponent, so the geometric series is out. N is all over the place as well. This would be hard to work with any other method. And if we try the test for divergence, the limit of this thing is 0, which would just mean the test fails right away. The way we can tell that the limit is 0 is it's a degree 1 in the numerator. Denominator is n squared to the power 3 halves. That functions like degree 3 in the denominator. The denominator is much more higher in degree, which means the limit of this whole thing is 0. So test for divergence is out. Sadly, that's why we're going to use the integral test on this one. Here's how it starts. We see the series, but we immediately change it out for a function. So we'll say let f of x be defined as x over x squared minus 4 power 3 halves. We have to give it a specific domain. Here's how the test is indicated at the start. I will say for us, on domain, not 1 to infinity, we're going 5 to infinity, just to match up the terms of the actual series we're looking into. And this one didn't have to start at 5, but it looks like it's trying to avoid maybe 2 specifically. You wouldn't want to start this one at 2, because you would be dividing by 0 right at the very first term. And it's starting at 5, could have started at 3, but we'll match it up right here. Next thing we take a look into is the hypotheses. On whatever domain you specified, ours is different than the one in the theorem above, we need to check those values or those conditions right here. Let's say below, then f is continuity. On this domain, yes. On that domain, no. We lose continuity right at 2. But this function does maintain continuity on that domain. Let's just assert f is continuous. Is it a positive function? No. Unless you restrict to this domain, it absolutely is. We took this domain to include any negative numbers. Immediately, we would lose positivity. But when x is from 5 to infinity, every value that we plug in here, starting at 5, gives us a 21 in the denominator, only involves positive values. So I'll say here, f greater than 0 for that second part, positivity works. Actually, you could weaken that. It could really be weakened to non-negativity. So it could be that, for example. But that would be kind of weird because your function can't hit the x-axis and ever come up like that. But if you did weaken to something like this, it would still be appropriate for the test. So we have positivity. Last one is decreasing, and decreasing isn't always easy to check. Sometimes you might be motivated to use first derivative test for increasing, decreasing. You would take the derivative of this, and you would have to say the derivative is always negative for all values in the domain. That's the official way to go, and it's actually a pretty long problem in its own right. But the same methods we use to take limits also applies here. If the numerator is to degree 1, and the denominator is effectively to degree 3 because of the power 2 on x and the power 3 halves here, this is a decreasing function. For large enough values in this domain, denominator increases so rapidly respect to the numerator that it is going down, decreasing. So let's just assert and decreasing. This part we wrote in black is all about condition checking to know if we can use the test. It's something you ought to get in the habit of writing down on paper. If you don't write it down on paper, I'm not super worried about that, but at least have the thoughts in the back of your mind. If you're going to apply this test, writing this down is for the sake of safety, that we didn't miss any weird thing that could block this. For example, that's a weird series for sure, but if it looked like that, we could actually test this one when we have enough tests. But this does not apply because now it's an alternating series. It doesn't have the positivity. Sometimes it's positive, sometimes it's negative. So writing these down on paper is just a form of protection so that we don't accidentally misapply the test. But because all these work, we now, well, there's two conditions, but really all we're doing is that improper integral. We'll see if it converges or diverges, and then make the corresponding conclusion we see on the right. So next, integrate. It's an improper integral going from 1 to infinity of f of x, whatever the function was that you defined, dx. We have to use the ordinary correct limit notation for this kind of problem. So we'll also say this is limit, not as n. That's just a weird habit now that we're in sequences in series. Limit as t goes to infinity. Integrate from 1 to t. Let's input the f of x function as well. X over x squared minus 4, power 3 halves, dx. So that's our next step right here. And just as a comment that we have for helping when it comes to doing this as an exam, recall we must show this setup. It's not worth a lot, maybe 1 point on any problem, but it's a point that also could be taken off an exam where 1 point on exam feels different than homework for sure. So that's just a comment to help out with doing the problems in an exam setting. At this stage, we're just doing an ordinary integral. It's like we're back in section, what was that, 7.8. How would we do this one? Looks like a good u substitution, right? We have x squared in the denominator, x in the numerator. Yeah, question first. The lower, oh yeah, absolutely. Thanks for spotting that. That one should have been corrected to a 5. That one deserves a color that kind of pops out. 5 here, 5 here, because of that there. Good, thanks for spotting that one. That one was going to cause multiple problems because we would have improper type 1 and type 2 if we go from 1 to infinity. There's a discontinuity inside there. Other questions or comments at the moment? Okay, with that big correction on the lower limit of integration, we can now say, let u through u substitution be x squared minus 4. Du is then 2x dx. Or we could say a half du is x dx. So the x dx right here can be eliminated. Up to you at this point if you want to change limits of notation, the limits of integration or not. If you do change them, it would look like this. X from 5 to t, but write them out in the same orders for safety. Changes to u goes from t squared minus 4 to 25 minus 4 for a 21. So let's put all that together. Finalizing this integral, we have the half du coming out. So here's 1/2 in front of even the limit. As t goes to infinity. These are our new limits of integration, 21. T squared minus 4. The x dx became the half du. So here's du, and now we have all of 1/2 du. And the remaining part is 1 over that to power 3 halves. But we want to bring that into the numerator, so we could also just rewrite it as u power -3/2. So we put in place of there u, but then we just drew it up into the numerator so we can integrate cleanly on the very next step. Any questions, folks, with the setup to this stage? Okay, now we do the standard trick here to integrate. First, I have a 1/2, a little bit more space than the limit, because the limit is still alive and kicking. Now at the red dot, antiderivative is u power -1/2. Take that coefficient, multiply by the reciprocal. I'm putting it way outside, even in front of the limit. Let me fix my negative signs first, just so it's not a distraction when we go to evaluate this right here. So this evaluation is the fundamental theorem of calculus, because at the moment, t squared is a real number, it's larger than 21, but then we're going to take the limit. So this becomes negative of a limit as t goes to infinity of, we're plugging t squared minus 4 into that thing. But because the power is negative, you could just drop it to now the denominator, put t squared minus 4 here. So I've done two things: substituted in t squared minus 4, took in the negative exponent, forced it positive, so I took the whole base, dropped it into the denominator. Do it one more time, this will turn into 1 over 21 to power 1/2, or just square root 21 if you prefer. I left it as the power 1/2 just to show the change from negative to positive without doing too many steps. Finally, we're about there, folks. We take the limit as t goes to infinity. No effect on that one because it's a constant. But over here, we have a function that grows to infinity in the denominator, but totally constant in the numerator. This whole thing would converge to 0 in a limit outright. Does that make sense to folks on the limit there? Awesome. That means we're done with the limit. We have 0 minus this, an extra negative sign that gets distributed in. So this is positive 1 over square root 21, which means it converges. But that's not the major thing we were trying to resolve. All I've said right here is the improper integral from 5 to infinity is a convergent one, and that's the value it converges to. But the larger conclusion is way up here. Let's use the fancy therefore, because this was a lot of steps. Synthesize all of this work, even at the very top, and we can say summation from 5 to infinity of the sequence n squared minus 4, power 3/2, must also converge by the integral test. And that's our very first one. Most steps of the integral test are quite a lot. You can streamline this a little bit. You still want to define the function. You still have to integrate. This is good to write down on paper, but if you do a lot of them and you don't write it down, I'll just assume that you looked into it and you checked off those things mentally. And the integrals are always too bad. This one looked a little bit more involved just because of the u substitution in the middle of it. Well, we did it, folks. This is a really powerful procedure. When it works nicely, but it is totally dependent on how approachable is the integration part in the first place. Another follow-up concept about this is an infinite sum, and computing what it converges to exactly is really tough. It's easy to estimate, though. That's the estimate. I can say that the total sum here is less than 1 over root 21. So that's kind of nice in a way to have that estimate. Other things that this section does discuss is error bounds on those estimates, but we're not going as much into the error bounds properties. We're mostly discussing the convergence divergence so we can use these methods elsewhere. If you're curious though, estimates on how reliable 1 over root 21 is in estimating this are interesting concepts that do get picked up again in a follow-up class called numerical analysis, looking into the reliability of these kind of processes. But that was just our first problem. We need to do it all over again, so let's try it out on this one. Not the friendliest looking problem though, right? This is a callback to something that happened in 11.1, 11.2, and now 11.3. And the reason we do these problems at least once per section is when we're back doing Maclaurin series, Taylor series, this whole process of coming up with a pattern is something we do on essentially every single problem. So we're starting early with this kind of analysis. Because it's being added infinitely many terms, that automatically tells us it's a series because of the dot, dot, dot. Not a partial sum. This is the whole sum we're trying to consider. So let's say it's equal to a summation from any index we want, but let's just say this is the first one. Natural to say 1, go off to infinity of an. We need to discover the nth term of the sequence an. Or you could say the nth term of the series here as well, if you prefer. This one is not as bad. There's a bit of a process to this one, because the key feature about this particular set of terms is the numerator is always 1. All you're doing then is analyzing what's changing in the denominator. Anyone see a pattern that jumps out at you right away? Exactly, it's a generic +4 kind of pattern. So that is a huge observation on this one. If we're increasing by 4, then you might want to do something like, how about increase by 4? How about 4n? Does that make sense? Sorry, say again. 4 written that way?
Oh, no, 4n and then separated -1.
Gotcha. So 4, oh, that's not Control Z. There we go. 4n and then a -1. So this is going to capture the part where it's increasing by 4 because each n we put in, that's an additional 4 added in. We also have to convey, there's a starting point as well, right? The 3 right there. So we could take that 3 and say 3 plus 4n minus 1 and see how we did. So let's take a look into this. We're not saying we have a guaranteed right answer right on the very beginning, but just like anything, it's kind of a trial and error process. But this kind of process has a definite starting point. Should be something about like that. If we throw in 1 on that, we get 1 over 3 plus 4 minus 1, which gives us 1/6. Means we need a small fine-tune adjustment in here somewhere. Or maybe here, something about the denominator needs to change a little bit. Anyone see what the correction could be? If we take off the 3, let's give that a try. So the 3 gone, it's gone from here and here. A1 would give us 4 by 1 minus 1 per third, and we nailed the very first one. Then the statement we always make here is never celebrate early, right? Be hugely skeptical and critical. Try out A2. Throwing in 2 here will give us 1 over 8 minus 1. And so we get a 7. We've landed on the second one. It looks like this is doing pretty well for us. So let's try this one at A3. We throw a 3 there. 1 over 12 minus 1 for a 1/11. At this point, I'm convinced. This looks like it's the right format for the series. An should just be 1 over 4n minus 1. We now visually inspect this, put 1, 2, 3, 4 inside. 16 minus 1 is 15. Put 5 inside. 20 minus 1 is 19. And that means we've got it right in this format right here. We never use the 3. This is just the right format in the very first place. Kind of weird, right? I think what I was thinking of when I put down that 3 was an as 1 over 3 plus 4, maybe it was n minus 1. But if we went that route and we simplified algebraically, we'd get 1 over 3 plus 4n minus 4. And that would have been 1 over 4n minus 1, exactly what we have right down here. So this could have worked as a start out, but if you land on it from any other method, that's totally fine as well. We got there, but that's all that matters. We now know what this bit is. So it's like this is the point at which the problem can actually start. We'll say summation from 1 to infinity. An is now summation from 1 to infinity of 1 over 4n minus 1. Any questions, folks, to that stage? Okay, you always want to be a little bit critical when you see a denominator that could potentially be 0, but this is a 0 at a value of 1/4. So starting the index at 1 at any start would be totally fine on this one. Now at this stage, we define a brand new function. This one, however, you might guess, is it convergent or divergent? It's based off the power in the denominator. That's a power 1, so it means it seems like it feels like a 1 over n. It's almost like a harmonic series, right? There's just a linear combination 4n minus 1. But if this one diverges, the power here is the same, I expect divergence on this one as well. So let's hit it by doing this. Let f of x be 1 over 4x minus 1 on domain. We're going from 1 to infinity on this one. Then our standard check on the assumptions of the test, the hypotheses that allow us to use it, is that then f is, well, the discontinuity is at 1/4, and we're skipping right by it. So we're good on that end. It is continuous. This function starting at 1 gives us 1/4, and at higher values, it does get smaller and smaller, but they're always positive. So we can say there's positivity. F greater than 0 is now saying every value on this domain, f of x, is positive. So this is just a fast way to say it. And also decreasing. Decreasing because of our common argument, constant in the numerator, as something that's going to get larger and larger on this domain without bound in the denominator. This allows us to use the test, and so here's our next steps. We need to integrate from 1 to infinity, f of x, dx, but that's not a bad integral at all. This one should be a lot faster than the last one. It transforms into now a limit as t goes to infinity, integrated from 1 to t of 1 over 4x minus 1. You can use a u substitution procedure like we did on the very prior one. But whenever you have something where it's power 1 and just a coefficient multiplying, this is a good opportunity to take the shortcut method that we've been discussing since week 1. Let me know how you feel about this. If you would like to see the u substitution method, I'm happy to show it. But if I saw this, I would encourage you to write out the antiderivative in this way. Take limit as t goes to infinity. This is just like a 1 over x, right? Antiderivative should be the natural logarithm of that x, except that it's 4x minus 1. If we check this through the chain rule, the derivative of the absolute value 4x minus 1 inside the logarithm does turn into that times 4 through the chain rule. We'd have to multiply by the derivative of 4x minus 1. So all we do is put in a 1/4 right here. And we've totally avoided the difficulty of even worrying about u substitution. This is always a great process to take if it's a linear function. If it was degree 2, I would always use u substitution instead, just to be extra careful. Evaluate from 1 to t, and you get a 4th. Limit as t goes to infinity. Throw in t in that location, and it's just natural log, absolute value, 4t minus 1. Then minus natural log of, throw a 1 in there for natural log 3. But we were considering graphs of these kinds of things in prior sections, I think section 11.1. The logarithm graph just increases up without bound as the value of t gets larger and larger. This one increases even faster with 4t minus 1 inside of there. So this whole entire thing is positive infinity just because of the natural log being in the numerator. If it looked like that, it wouldn't be positive infinity. It would be negative natural log 3 divided by 4, which would be suspicious because it can't come out negative, right? If the function was positive. But with a logarithm like that in a numerator, that's our foregone conclusion. Integral diverges. And then after we have a conclusion of divergence, the conclusion for the series AN is always in the same direction. So here's our larger conclusion to say finally. We'll say therefore, once I figure out what's wrong with this, there we go. Therefore, summation AN, as n goes to 1 to infinity, must also diverge by the integral test. And we finally did it. Notice one thing we did though, we didn't even call back the original series, or definitely not that one. Writing that down is tedious. We just used this as a placeholder, kind of like a variable. And even though it looks weird, it's appropriate to write it in that way as well, because in context, we know what the subscripts should be when we write it out. We'll use this a little bit more and more, mainly because the further we get into chapter 11, the author uses these kind of shorthands as well. As the test gets slightly more involved, that's a great shorthand to use. But any last questions at all, folks, on the full rundown of this one? Okay, at this point in the notes, and this point in chapter 11, we get to do something that we've been mentioning a lot, the harmonic series. We keep saying it's diverges, and the fact that we say it's divergent is really critical now in section 11.2. We use it as a counterexample to show certain theorems don't reverse their logic. So the fact that the harmonic series is a divergent series is actually super important. And also notice what's going on in example 2. It's kind of a vocabulary question. You have to know what a harmonic series is in the first place. So let's make a statement right here. Any series that has a name must be memorized for exams. Because this kind of stuff will come up again. You have to know if we say harmonic series, which one we're talking about specifically. Another named series that we haven't discussed yet is this one. With that comment, it should be a good idea to name these. And there's only 2 series with names. So there's the harmonic series we're about to describe. And then there's this one, summation as n goes from 1 to infinity. Negative 1 power of n divided by n is called the alternating harmonic series. So I only have 2 named series that we have to be aware of in an exam setting. This is one of them, and it comes up in the next sections. It's actually a hard one to test because you cannot use the integral test on it. There's negatives inside here. It's an alternating series. The function you define wouldn't be positive. It also, you cannot use, say, test for divergence. The limit of this thing is 0 because the numerator is bounded. Denominator grows without bound. It's not a p-series. It's not a geometric series. That one is suddenly really hard to test. We just need more methods. But if you're really curious on what happens to this one, this converges. The alternating nature of this allows for convergences, and it's a surprise because this one, the harmonic series, is a divergent one. It's a sum from n equals 1 to infinity of just 1 over n, and we claim it diverges. The author gave an argument, but we're going to give a different argument. So it's now time to really assert, why does this diverge? We'll show it specifically. Maybe it makes more sense why this one converges. All of the terms here are positive, so it just keeps growing and growing. But the first term here is negative, negative 1/2. The second term is positive 1/3. So you drop down negative a half, but then you crawl back up. Then you subtract a quarter, you drop down, but then you go back up when you add a fifth. The fact that it's alternating is what it allowed a convergence on this one. But we'll look into that in a lot more detail in the next sections. For the moment, let's focus on the actual harmonic series and why it diverges. Not exactly easy to test until we have the p-series test. This resolves it. Our author proves the whole p-series test by using the integral test in multiple different cases, depending on what the value of p is. So it's a pretty long example and derivation. We're just going to do it for one case. Power is 1, making it the harmonic series. We begin by defining a function. Let f of x be equal to 1 over x on the domain from 1 to infinity. You usually don't want to put a bracket on infinity. Let me fix that. Now our assumptions are that we have to check. Then f is continuous. I'll just write CONT for continuous. Not exactly, but yes on that domain. We skipped past the continuity, which is at 0 for this function. So we have continuity. On domain from 1 to infinity, we have positivity on f, so f greater than 0. And absolutely f is decreasing. The graph looks essentially like this. So automatically decreasing like before. But same argument as before works as well. The numerator is constant, and the denominator only gets larger for larger values of x. We have f is decreasing. Now we just have to integrate, but it's a pretty fast integral. We'll go integrate from 1 to infinity, f of x. Dx is a limit as t goes to infinity from the integral 1 to t of 1 over x. This one almost feels like deja vu, right? We solved a slightly harder integration problem, 1 over 4x plus or minus 1, I forget. This one just becomes limit. T goes to infinity, natural log, absolute value of t from 1 to t, which is then the limit as t goes to infinity of natural log t. I dropped absolute value because of the t heading off to infinity implies positive. Minus 0 because plugging 1 inside here gives us natural log 1, which is 0. But it almost doesn't even matter if I put that there because we now have that this is equal to infinity, equal to infinity, so it diverges. I guess try to say infinity and diverges all at once. That doesn't work. But that's our proof. Sure, we waited till we had the integral test, but the integral test didn't cause any circular reasoning there. So we have a strong conclusion. Therefore, the harmonic series summation 1 to infinity, 1 over n, must also diverge by the integral test. And in a way, that's really satisfying because if we're going to rely on this as a counterexample and a prototypical example of divergence, we have to really show it at some point, and we finally did. It took a while to get there. So there's two interesting series. Always keep in mind, alternating harmonic series and the harmonic series are strongly related. You just have something alternating in sign in the numerator. But when you alternate, you have convergence. When you take the absolute value of that, it's now a divergent series altogether. Really very weird, especially when the limit of the sequence goes to 0. But now we can take this one fact here with the integral test, do some more clever integration, and go from something that was 1 over n, and now put in a power. We know at power 1, it's diverging. If it was power -1, it would have looked like this. It'd be the summation as you go from 1 to infinity of just n itself, and that grows without bound, diverges to infinity really quickly. So that's where this starts to make sense. In the P-series test, we have divergence right exactly at power 1, that's our harmonic series, and for all powers less than 1, including the negative ones like we considered right here. Divergent always in that case. And then we have convergence so long as the power is positive, greater than 1 specifically. This test is a wonderful test to use. I encourage you, whenever you look at a series, think in terms of these tests here. Is it going to fit as a test for divergence? If so, you absolutely should use it. Even if you're in section 11.3, 11.4, 11.5, work with the idea of it's all about parsimony. Take the simplest test, and it's the best one to apply. If it doesn't work, try the geometric series test. If it's not a geometric series, try the P-series test. But like we mentioned before, now that we have the P-series test, we have to be extremely mindful of this mismatch of directionalities. Convergence is totally different for a geometric series and a P-series. This causes a lot of trouble because whenever directionalities get mixed in your brain, you really have to resolve that. It's all about telling the difference between the two. Always remember, geometric series has n as an exponent. P-series has n as a base. That's the best way to tell apart why convergence is essentially backwards in a certain sense. But with that in mind, here are the problems for the P-series test. We're going back to kind of mixed problems where for each problem, we've been doing this all along, but just to re-emphasize, we have to give a final conclusion, convergence, divergence. For each one, we have to state the name of the test we use and show all steps of that chosen test. We're repeating this a lot on every homework assignment, on a lot of the homework problems as well. Just as a reminder, this is how these would be graded as actual exam questions. So that way we're ready for what the grading rubric would really look like. But here's how it goes. The base n is, or excuse me, n here is a base. It fits this format. That means it's a P-series. And even though I didn't say P-series test, you've implied the name of the test we are using. So that qualifies for this part right here. You absolutely have to show all steps of that chosen test. But the steps you actually show depend on the test. If it's an integral test, you have to show all of this. You have to integrate, you have to show the setup phase, converting to a limit, evaluate, give a conclusion, then go to the next conclusion. But if it's a P-series, showing all steps means this. You have to tell me what the power is, 1.0001. Go back to the test, greater than 1, and you have shown all steps. Kind of nice in a way, right? This is what we love about P-series, and this is why you're discouraged from using the integral test on everything. It works here, but why show all that work when this is all you have to say to show all steps? Last thing you have to do is give a conclusion as well. Double check all of these. Convergence for P-series is power greater than 1. That's greater than 1, just barely, but that's all it takes. We could put as many zeros as we want inside there, and it still converges, except it'll converge fantastically slowly with lots of zeros. But we'll say converges, and we are done. Kind of weird, right? These problems in chapter 11 are kind of spiky, from high difficulty, lots of steps, to not much to say, low difficulty, almost no steps at all. And this is one of those low level kind of problems in terms of difficulty. Any questions at all, folks, with the full conclusion and write-up? Okay, let's try it out again. Notice that this one's in the wrong format, though. It's easy to say diverges because the power is less than or equal to 1, but it's the wrong conclusion. N as a base has to specifically be in the denominator in order to use this format and those values right here correctly. So on this problem, there is an additional step. We'll write this as a summation from 1 to infinity. 1 over n, power positive 5/3. Now we know exactly what the power is in the P-series test. So to state the name of the test, If you call this PST, that would be P series test. Let's take a look. That would work for this one, and nothing seems to conflict in an acronym for that. So if you call it PST for P series test, I'm totally fine with that as well. In the notes, I'm going to usually try to avoid that just for the sake of clarity, but I just want to convey you don't have to say every part of it. You can use a couple shorthands here, and it's totally fine. So let's say P series test. So now we just said it, the full name of this test. We have to show the steps, and the steps are find the power. Here it is. P is 5/3. 5/3 is greater than 1. So now we give our conclusion. Converges again. So really the only danger in part B is you have to look before you leap. If you know it's a P series and you're about to use that test, look at the structure of how the P series is indicated inside that test. We have to match up that structure before we can actually give the right conclusion. So that was the only thing new in part B. What's new in part C is that it's just the same kind of thing, way more annoying. N to the power e minus 1 divided by n power pi minus 1. Let's rewrite this by doing this strategy. Give it a new name, call this summation an. This is now one whole symbol with this as a variable. We could pop it out as a brand new symbol. Now we're talking about the nth term, which is n power e minus 1, n power pi minus 1. I think it's just an exponent work problem, right? We still want to match this up, bring the base to the denominator. So this will be 1 over, let's take n to the power, if I'm keeping base n in the denominator, we keep those values right where they are, pi minus 1, and then we subtract whatever this exponent was. Annoyingly, it has 2 terms, so we have to be very careful with that subtraction. But that's what the structure would look like. Just an analogy, because this feels so abstract out of nowhere, it's like doing x cubed over x power 5. You just go 1 over x power 5 minus 3. That's what we did, but extra level of abstraction with all those interesting constants and symbols. Now that we get to that stage, we can write that this is equal to 1 over n to the power, let's see, it's pi minus 1, but when we distribute the negative sign, this is a plus 1, canceling that. It's just pi minus e. Okay, that's a little bit annoying as well in its sake, but keep in mind, you can do some interesting estimates or just grab a calculator. It's allowed in exam settings. Pi minus e is this figure, approximately 0.42. So we're about ready to satisfy the whole test. Pi minus e, approximately 0.42. More importantly, it's less than 1. Convergence is at greater than 1. And notice when we give these conclusions, it's a good idea to always write out this. You would get full credit if you said P is 5/3 and converges. But when you write this down every single time, you're just forming a neural pathway that reminds you convergence is at positive 1, this is at divergence. In fact, you should really say it this way. Less than or equal to 1, it seems silly, but again, you're just reminding yourself, you're forming an actual neural pathway to remind you divergence is at less than or equals to 1. If you do that every single time you do a homework problem, it's like automatic in an exam setting at that point. So let's run through the full test now. We can say summation an is really a sum from 1 to infinity, 1 over n to the power pi minus e. Like before, we'll indicate the test we're using by the P series test summation an diverges since the power we found is P pi minus e, and it's less than or equal to 1. Notice how I stated the information right here. It's kind of backwards from all the other ones, but I did say the test we're using, I guess not totally backwards. I did say the conclusion, and then I showed the work. You can give these in any order that just feels natural, is what I'm majorly trying to convey. As long as you name the test, give the conclusion, show whatever the work is relative to that test, you'll get full credit each and every time. So that one is kind of sneaky because it's easy to make a simple mistake right here, but it really was a divergent sequence. Any questions at all, folks, on finalizing that one? Okay, well, power series are great. So are the geometric series and anything that fits into the test for divergence. So far, this is what all of our tests look like. This is everything on the table up to section 11.3. Test for divergence, geometric series, power series, integral test. There was one other method where you can split up two convergence series. That's in section 11.2. And for example 3, these are now all mixed. It's up to us to decide what method fits with what problem. And that means it's a good review type of problem. Every time we start picking up more and more tests, we're going to wrap up with a kind of review subsection because our major goal is to learn how to tell between all the different kinds of series, all the different kinds of tests, so that when we start doing things like absolute convergence, and when it involves a bunch of other tests all at the same time, we'll be way more fluent on how to pick out the right one. So it's not about learning the tests in isolation. It's all about telling them apart and seeing which one to use at the right time. I think this is a good one to come back to after the break. We'll have a good review session right here before we move into section 11.4. That's going to be on March 31st, it looks like. But I guess this is a good stopping point for us, folks. Any questions at all with where we ended up at? Okay, so that's sequences and series so far. There's always rough spots, and then there's nice spots like the P series. That'll be the experience for the whole chapter 11. But have an excellent vacation, folks, for spring break. I realize it's not really a work vacation necessarily, but have a great vacation from school. And if you're still working, if you're getting caught up on homework and you have questions, I am available by email. I'll be checking it every morning. I'll be happy to work with you to help you out if you are working yourself. Otherwise, see you all in a couple weeks. Yep, take care. Thanks, you too. Try not to work too hard.